Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be covering polar bonds and how you can go about determining them. Let's get started. So if you recall in previous videos, I introduced these type of bonding that can occur between nonmetals as a covalent bonding. Covalent bonding meaning we're sharing those electrons. We also talked about ionic bonding where we're actually transferring electrons. Well, this idea of bond polarity is going to be associated with covalent bonding. Remember, in covalent bonding, we're sharing our electrons. Now, just because we're sharing electrons to both meet our octet does not mean that we are going to be ultimately sharing them evenly. Just like what happens in tug of war, you can have someone pulling their electrons closer to them, or someone that's not able to pull as tight, so they're going away from them. And what you end up with is uneven sharing of these electrons. When you have uneven sharing of electrons, the electron cloud becomes distorted. And so you no longer have a nice symmetrical cloud. Instead, you end up with a cloud that's distorted towards the area that more pulling is occurring. That's distortedness that's happening with these electron clouds. That is what we know as a polar covalent bond. So in a polar covalent bond, you're looking for this distorted cloud that's going to exist, where the larger end, that larger electron region resides with the element that's able to pull the electron towards it. And overall, you end up with this partial or pseudo negative charged area. And then the other end ends up with this pseudo positive charge or partial positive charge that occurs. Now notice I'm saying pseudo or partial. These are not ionic charges. I'm not actually transferring the electron. I'm just pulling it a lot closer to me. So if I have the electron pulled closer to me, I'm going to overall have a more negative area surrounding me. And so we see this happen when you have elements that have a difference in their strength or their ability to pull their electrons toward them. And so look, for instance, here if we're dealing with something like HF, hydrofluoric acid. And so in this case, you can see that the electron cloud is quite distorted, right? With more of it favoring towards the actual fluorine atom. All right, and so over here is where we would expect our negative charged area or partial charge area. And over here would be that partial or pseudo positive region that occurs. And that charge that's present can align and be attracted to different portions of the magnetic or the electric field, similar to what happens in ionic compounds. But again, they are not true charges. It's not like an ionic compound. Now, there is some parallelism to this idea of polarity and up to their ability to become ions, right? So in a polar compound, we have uneven sharing. That means I'm pulling more of my electrons to me, right? The shared electrons are coming towards me. Well, in an ionic compound, when we're dealing with these ionic compounds, I have not only just pulled it from you, I have taken it. And so now I have this much more the defined negative region, and you have this defined positive region. So polar compounds are on a scale or on a spectrum of an ionic character. They're creating these partial positive and negative regions, but they're not quite to the point where they've created true charges. And so you want to keep that in mind as you're classifying the different types of bonding that are occurring. Do we have even sharing where we're both pulling it evenly? Am I pulling it a little bit more, so now we have uneven sharing, or have I completely taken it from you and now we've created an ion? And so there's a range of ionic character that can exist within these compounds. Now, the big thing that plays into understanding, will I have a polar bond occur, or ultimately will an ionic bond occur, is this idea or concept known as electronegativity. So electronegativity is an atom's ability to pull electrons toward it, okay? And the trend for electronegativity, if we think back to how our trends are set up, is going to increase across the period towards your nonmetals. Remember, they like to get electrons. And it's also going to increase up the periodic table, okay? With your most electronegative atom being fluorine. The least electronegative is francium on the other corner. And noble gases are not assigned values because remember, they don't want any electrons. They don't want them at all, okay? And if there is a large enough difference between electronegativities, that's when you're going to end up with polar bonds. And then if it's so large, that's when you end up with ionic bonding occurring. All right, and so you can see a scale here of different electronegativity values that you would expect for different atoms. And notice again, on your nonmetal side, that's where you see far more present compared to your metal side. Okay, so increasing towards fluorine. So we can actually do a quick calculation if we are aware of the electronegativity values to figure out if something is purely covalent, meaning we're evenly sharing, nonpolar covalent, meaning that we're not necessarily sharing exactly evenly, but it's not really distinguishable either. Are we polar covalent, meaning there's uneven, or are we ionic where I've now taken it, okay? And so the calculation we can do, we could subtract the two electronegativities that we know and look to see what the difference is. If there's a difference of 0, then we say that it is a pure covalent substance. If there's a difference between 0.1 to 0.4, that is a nonpolar covalent, meaning it's uneven sharing, but it's not really that defined, okay? So we're kind of going back and forth. If the difference is between 0.5 and 1.9, well, that's where we have a polar covalent compound. And again, that means uneven sharing. I'm pulling it more towards me. And then if the difference is greater than 2.0, that is where we have an ionic compound being created. So we can see this demonstrated beautifully in this picture here. And so if we look at something like Cl2, chlorine gas, we know that those two atoms would have the same electronegativity value. And so if they have the same value, if we look at the difference, we expect 0. And so as a result, you see the electron cloud is evenly distributed across those atoms. So this is a purely covalent compound or a purely covalent bond. Now, if we look at something like hydrogen and chlorine, if they came together to form a compound, well, the difference in electronegativity is about 0.9. And so that falls within that range to say that this is indeed a polar bond. We have those pseudo-positive, pseudo-negative regions that are created within this molecule. And again, that distortion is pointing towards the more electronegative atom. And then if we look at something like sodium and chlorine, where we now have an electronegativity difference that is greater than 2, well, now chlorine has completely taken the electron from sodium. And as a result, we end up with an ionic compound with the positive and negative species that can be attracted to one another. Now, there are these things called dipole moments that we represent on these polar molecules. And so the dipole moment is simply the measure of the bond polarity. When we're drawing the dipole, that word dipole is indicative that there are two poles, two opposite ends that exist, this pseudo-positive region and the pseudo-negative region. When we're drawing it, we again draw that dipole in the direction of the more electronegative atom, where the crosshair represents the positive side and the arrow points towards the more negative side. Generally, the more electrons two atoms share and the larger the atoms are, the larger this dipole moment would be. And the percent ionic character is the ratio of a bond's measured dipole moment to what it would be if it were completely ionic. And you can see some different dipoles associated with these different compounds that exist, where we see that how it increases as we change the different type of bond that we're dealing with. All right, so let's make a prediction here. So the question is asking us to determine whether an N to O bond would be ionic, covalent, or polar covalent. And so if we had information about the electronegativities, we could say and look at, well, what's the difference between them? The difference between nitrogen and oxygen would be only 0.5. So it's a small difference, but it is considerable enough so that it would not be considered nonpolar or purely covalent. And so when we look at that difference, it actually falls in the range of being a polar compound. And so we would anticipate that this overall would be considered a polar covalent compound or polar covalent bond. I hope this information helped you understand polar bonds and how to determine them. Make sure you guys like, comment, and subscribe, and let me know what other material you'd like to see. Make sure you guys come back and see other videos, and I'll see you guys in future ones. Have a great day. Talk to you later. Bye-bye.